Well, hello there, Pre-Calculus 2 class. This is Mr. King, of course. I hope you're all doing well and you are seeing some light at the end of this long and but short tunnel of your Summer 2 course. I would like to continue our discussions, of course, on from Chapter 6. This is Section 6.3. And this will be about a new topic, some new concepts called vectors. And it's a two-section introduction to vectors. And as I just mentioned, it's an introduction. We don't go too far into all the usage of and applications of vectors, just the introduction. Okay, so I hope this will, if you need help, I hope this will help you, and let's do some mathematics class, okay? So I'll take us to our WebAssign page, and we'll begin. Okay, then, Pre-Calculus 2 class. So here we are on section 6.3, as I mentioned in the intro, an introduction to vectors, and I think problem 6 is a good problem to start out. And I'll use this problem to introduce the basic idea of vector, what a vector is, and some terminology and notations, as well as answer the question. Okay, so here we go. Excuse me. So they give us a vector, two of them, even though we don't know what the heck a vector may be yet. And they like to use letters U and V for some reason. I can understand V, vector. Anyway, so they pick letters kind of close by the alphabet, and right around here in the alphabet, U, V. So anyway, and then they give us where the vector begins, which is called the initial point, and then where the vector ends, which is called the terminal point. And they do that for vector u and also for another vector, a second vector v. So we're going to draw these points on a coordinate plane, an xy coordinate plane. And then these are the first four parts to this question. And one of them is, what's the slope of the vector u? What's the slope of the other vector, second vector v? And we'll just use our rise over run formula. If we have 2 points, which we do, initial point and terminal point, we'll just use rise over run. And then this little symbol, it looks like a double absolute value symbols. The two vertical lines on each side. Inside is the vector u. And this simply means it says here the magnitude, which means the length. How long is this? How long is it in a straight line from this initial point to this terminal point? Or we can say what is the length of this line segment from initial point to terminal point, which we also can say is the vector. Okay. So let me take you to my notebook, and here we begin. So the number 6, the given, the vector u, vector v, when we, excuse me. So in terms of notation, in textbooks, they have the option to make the text bold or not. And notice for vectors, they make it in boldface type. So it's darker here, thicker. And for us, well, unless we wish to try to make it bolder and a little thicker on our paper, otherwise, the common notation is to put your letter, vector v, and put this little, it's supposed to be kind of horizontal here. I always tend to make it a little slanted, and then a little half of an arrow, and that's the symbol notation for vector. And the same thing here. I may not be very consistent, but that's what we shoot for. Okay, that one's not bad. Okay. So let's talk about the vector u. And we're using this, as I mentioned, as an introduction to lots of terminology, notations, and so forth, as well as answer the question. So let's take a look at vector u. The initial point, I'm going to call it, it's typically authors call for vectors the initial point P, the terminal point as Q, in a x, y, two-dimensional coordinate plane that we're used to working with. Here's the origin, of course. So let's see. The initial point where the vector, or there's another name for it as well, a directed line segment, which just means, because this is one endpoint, this is another endpoint, if you connect them, you have a line segment that doesn't go on forever in either direction. And the initial point, because it's not only is this a line segment, it looks like one, that's for sure. So what is he talking about? That looks like a line segment. It is a line segment. What about the directed part? That means normally lines, when you say a line segment, you just have you have two endpoints and then you connect them with a line. But the line doesn't continue past the endpoints. So it's just part of a line or a segment of the line. So direction, the directed means which way would we be drawing this directed line segment or this vector. So depends on what the initial point is and what the terminal point is. Which one is which? This one's the initial point, P, which is 4, 0, which is right here. The terminal point, 9, here's the origin, 9 over on the x, in the x positive x direction. The second dimension value is y equals 3, positive 3, upward 3 units. And so there is the terminal point Q, 9, 3. And so in terms of directed line segment, we say directed line segment PQ with this vector symbol on top of it. So this is a directed line segment. So again, I talked about the terminology here. I think for these two introductory sections, it's enough to say, without being overly complicated, unnecessarily complicated, that a directed line segment represents a vector. Or you can even say it is a vector. So there is a slight definition that is really not that important, so I don't think it's worth mentioning at this very introductory moment. Maybe I'll mention it later. If not, it's not a big deal for now. In Calculus 3, you talk about vectors again, and then they right away in the first paragraph they talk about, well, I'm going to wait for time. So we have directed line segment PQ, or which because it's directed, then that means it's a vector. A vector is a line segment that has direction. Yeah, they're sort of interchangeable. Okay. We're asked to find how long this segment is, which is the length, which we can use the length between 2 points in a coordinate plane, or the length between the length from one point to another, the shortest distance between 2 points is when you draw a line segment between the 2 points and then find that distance. Or we call it, for vectors or directed line segments, then they have a fancier word besides the length, and they call it the magnitude, the size, because vectors usually represent a force, some force that's being applied on an object or objects. So the magnitude, meaning the longer the directed line segment, then the more powerful the vector is, the more force it has. So magnitude means something as well in terms of its length. Means the magnitude increases as it gets longer, which means more powerful magnitude. So to find the length or the magnitude of this directed line segment, the distance between these 2 points, the length or magnitude of this vector, which we can say vector PQ, we can say directed line segment PQ, we can say vector U, that's what they're calling it. And then to do that, we just use the distance formula. And I'm going to call this one the terminal point 93. That will be our x2, our second x value, our second y value, and then P, the initial point, will be our first x value and our first y value. So let's find that length or magnitude of this vector u, or we can say of the directed line segment PQ. So I wrote this over here. The magnitude or the length of directed line segment PQ, which is the same thing as saying the magnitude of vector u, is equal to, by the definition of distance between 2 points in a coordinate plane, is the, well, one of them you call the second x value and the other one the first x value from your 2 points. We're going to call this one the second one because it's the terminal, and this one the first one because it's the initial. So the second x value minus the first x value, so that'll be 9 is the second x value, 4 is the first x value, and then you'll subtract 9 minus 4. So what that basically does is tells us the horizontal difference between the initial point and the terminal point. How far is it horizontally, which we call the run. And then the other part, y2 minus y1. Here's the second y value. It's 3 units up. The first y value just happened to be 0. This point just happens to be on the x-axis. It doesn't have to be. So we'll say 3 minus 0, which gives us the distance upward from this point to this point, the vertical distance. I know the point's not right here, but to get the vertical distance, you have to say it's the distance from here to here, which right here is the same height as over here. Or you can say from here to here. Well, if this is at y equals 0, which it is, and this is at y equals 3, which it is, well then this must be 3 units. It's also called the rise. So, how far is it from 4 to 9? Well, 9 minus 4. This is 1, 2, 3, 4, 5, 6, 7, 8, 9. So from P, which is at x equals 4, to right here is x equals 9. The distance is 9 minus 4, which is 5 units. And that'll be our run. Well, since I keep mentioning rise and run, and we have to find the slope of this directed line segment, it's just like finding the slope of, if we were to extend this into its line, then we could say the slope of the line as well. Or you can just say the slope of this line segment, or you can say the slope of this directed line segment PQ, or you can say the slope of this vector And what that does is it gives us the direction that the vector is moving, or the direction in which the force is pointing, I should say. Is the direction of the vector is the direction of the force that is being applied onto an object. And so that gives us the direction, this slope value. So from here to here, the slope is this amount of run and this amount of rise. The slope of the first directed line, I'm going to call this one the first one because that's the first one they gave us. The slope of the first directed line segment PQ using rise over run, well, the rise we just said was 3, and the run was 5 to the right. 5 to the right is a positive movement, upward is a positive movement, so 3 over 5. If you're wondering, what if I were to go the other way, then if you went downward, that would be a negative 3. Leftward would be a negative 5, but then the negative over negative would cancel out, divide out to positive anyway. So the slope of the first directed line segment is 3/5. What about its magnitude? So let's compute that. So we were right here, and I kind of changed course, start talking about this a little more. So we have the square root of x sub 2 minus x sub 1. The second x value is the 9, as we just talked about, minus the first x value is the 4. 9 minus 4, well, that's that rise. That's the amount of, that's the amount of the run. Excuse me. 9 minus 4 is 5, and you still have to square it. Plus right here, the difference between the two y values, y sub 2 minus y sub 1. The second y value is up here 3 units. The first y value is 0. So we have 3 minus 0 for y2 minus y sub 1, or subscript 1. So 3 minus 0 squared, which is the rise, which is 3. But then to get the magnitude or the length, we have to do this distance formula, which is now square them. 5 times 5 is 25, of course. 3 times 3 is 9. 25 plus 9 is 34, and then the magnitude or the length of this directed line segment PQ, or we can say vector U, is the square root of 34 units. Depends if they ask us to round our answer or not. Would we then put this in a calculator? And if we look, magnitude, and it doesn't say anything about rounding, so that means they want it left in exact form, which then means the square root. The square root of 34, we cannot take the square root of 34 because it's not a perfect square. And so the square root of 34, the slope was 3 over 5, we just said. And let's check that. So hopefully we have that correct. And there are those friendly green check marks. Okay, hope that's okay. Well, now we're going to do the same thing with the second initial point and terminal point that together makes a directed line segment again, or we say a vector again. And they call this one vector V. Vector V. So here are the 2 points, initial point, terminal point. So let me go to my notebook. So here's vector V, the second one. The initial point is -7, 1, or we'll say point P. So here we are in the same coordinate plane. Here was the first directed line segment PQ, or vector U, and now we're looking at the second one. Point P is negative from the origin, -7 in the x direction, leftward, and then upward 1 unit. So there's the initial point, -7, 1. the terminal point Q is 3, 7, positive 3 on the x-axis, and then up 7 on the y, in the y direction. And so here's point Q, 3, 7. And so let's call this directed line segment PQ, but it's the second one that they gave us. And I put a little subscript 2 there if we like, and then I was like, I don't know if that's going to confuse us, but shouldn't. So here's our second directed line segment PQ. And we need to know its magnitude or length. This is also the vector V. Starting point, initial point, terminal point, which means you can put a little arrow there. That doesn't mean that it's just that this is a ray that goes on forever, because that's what that usually means. But when we're in the discussion with vectors, then that just is telling us that this directed line segment is a vector, which means it does end right here, and here's the terminal point. But the direction is this way. And this little arrow then means not that it goes on forever, but this must be the initial point, and then this is the terminal point. And so this is the direction of that vector. Another way to describe the direction is we could use slope. We can also use, which is more popular, is to use this angle right here. And we'll do that towards the end of this lecture video. And then that ends up being far more useful than just the slope. So I think just the two introductory questions are asking us to compute the slope of the directed line segment or of the vector. Okay. In the next section, 6.4, well, I'm not positive. We might wait till, I believe it's towards the end of this chapter. But anyway, so we don't need to talk about this right now. So, yeah, so let's compute the slope of the directed line segment PQ, or in other words, vector V. So we need to know the run and the rise. This is run, rise. We could just count if we want to. This is over here at -7 units. So from here to here is 7. And this is over 4 units to the right. So 7 plus 4 is 11 units. So that'll be the run. And then from here upward to the same height that this point is at, Q is at, is the rise. Or you can say from right here to right here. This is up, right here is 1 unit up, which is the same as this. 1 unit up. And then this is 7 units up. So if you're at 1 unit up, and now you go this line, this goes to 7 units high, then from 1 to 7, that's 6 units in between. Or you can say 7 minus the 1. So that's going to be the rise, 6 units, 6 vertical units. Well, anyway, or we can use a formula. But we also need this magnitude. So let's do that. And, oh, yeah. So right here, also the magnitude of the directed line segment PQ, the second one, or which is also called the vector V, so magnitude of vector V, or the length. And here's the square root again, using the distance formula. X sub 2 minus x sub 1 plus y sub 2 minus y sub 1. We just did it a moment ago for the first one right here, and we got the square root of 34 units. Now let's do it for this one. Clearly this one looks longer. So let's see, this is the terminal point. So this is our, we'll call this one our second point, because it's the terminal one. So x sub 2, y sub 2. This is the initial point, so we'll call this x sub 1, y sub 1. So we're going to find to find the distance between these 2 points, we're going to say x sub 2 minus x sub 1. What that does is it gives us the horizontal distance this way. And then we'll say plus y sub 2 minus y sub 1. Y sub 2 is 7 minus y sub 1 is the 1 value. And that gives us the rise, the vertical distance between these 2 points. And then basically we're using Pythagorean's theorem. So anyway, so what is our x sub 2? It's 3. Minus what? Minus, what's x sub 1? Negative 7. So we got to be careful. So it's 3 minus always, and then what x sub 1 happens to be negative as well. So we have a 3 minus a negative 7. And that changes to 3 plus 7. And then you don't square it yet until you've simplified inside the grouping symbol. And 3 plus 7 is 10. So that's why we have right here, or square root of 10 quantity squared. And then plus y sub 2 is the 7 minus the y sub 1 is the 1. So plus 7 minus 1, quantity squared, of course. Simplify. 7 minus 1 are the 6 vertical units which make the rise. So plus 6 squared. Now just continue to compute. And we get 10 squared is 100. 10 times 10 is 100. 6 squared is 36. 100 plus 36 is 136. And it turns out the square root of 136 is not a perfect square. So if we put 136 in, it doesn't work out to an integer only. Not like 12 or 11. 11 times 11 is 121. So 121 is a perfect square. 12 times 12 is 144. 144. So the square root of 144 would be 12. But 136, no, it doesn't. This is not a perfect square number, so it doesn't work out here as an integer only. These numbers, these digits, numerical values of these digit places, or these are digits, sorry, they go on forever. They just don't show it here. So this is irrational, an irrational number. So instead of putting this down, they don't ask us to round it on our WebAssign, just like this one. So we're going to leave it with the square root. It just so happens that 136, though, we can split up 136 as divide. So you can start trying to see, can we divide this by any smaller perfect square? Well, let's see. 1 is the first positive perfect square, but that won't help. To write it as 136 times 1. 4 is the next perfect square. That's the next largest one. So divide by 4. And it does work evenly. So 4 times 34 is 136. So then, knowing that, change 136 as the square root of 4 times 34, knowing that you can take the square root of 4, which is 2. So you split it up now, the square root of 4 times the square root of 34. And the square root of 4 is 2. The square root of 34, 34 is not a perfect square like 25 is, and 36, and 49, and so forth. So we cannot take the square root of 34, and you can't break it down anymore so that into 2 factors. Well, you can, like 2 times 17, but neither 2 nor 17 is a perfect square, so we're stuck. So we need to leave it as the square root of 34. So it becomes 2 times square root of 34. That's the length or the magnitude of the second vector, which is vector v. So it turns out, class, this one was the square root of 34, remember, units long. And this second vector, v, is twice as long. It's twice this one. 2 times the square root of 34. So my picture is not scaled very well, obviously, because plus it's zoomed in. This is zoomed in on I'm blaming my camera. So, but it's a freehand drawing, so it's not going to be right. But it is twice as big, or twice as long as this one. Okay, so the magnitude of the second vector is twice the length of the first directed line segment PQ1, or we say vector U. Okay, so what about the slope then of this second directed line segment PQ, or we say vector V? What's the slope? Well, it's the we need the rise and the run. Well, we already did that when we did this right here, because the difference between here and here we just computed when we said the 3 minus the -7. And so 3 minus this number, -7, is 10. So that's how long the run is, 10 units. And this is the rise, which was the y2 minus y1, which was right here, and that was 6. So this is 10 and this is 6. So up here I wrote that as well. The slope of directed line segment PQ sub 2, or vector V, either way, is rise over run, which is 6 over 10. But 6 over 10 does reduce to 3/5. 3 times 2, 5 times 2, 2's divide out. You're left with 3 over 5. So the slope value of this directed line segment is the same as the slope of this directed line segment. Or we can say the slope of this vector V is the same as the slope of vector U. Or another way to say it is the direction of this vector is the same as the direction of this vector. These would be parallel because they have the same slope, which means they have the same direction. So, but do they have the same length though? They have the same direction, but they are not of the same length. Remember, this one was twice as long as this one. Okay, so let's read what I have here. Since the slope value of the second directed line segment PQ is 3/5, which equals the slope value of the first directed line segment PQ1, the two directed line segments have the same direction, as I just mentioned. Also, the length magnitude of these two directed line segment, or vectors, are, which we have already done by now. This one was double the magnitude of this one. Therefore, these two directed line segments, or vectors, they have the same direction, as we mentioned, because of the same slope. You're like, wait a minute, one was 6 over 10 and the other one is 3 over 5. But slope, you can reduce that fraction. 6/10 reduces to 3/5. So they are parallel directed line segments, or so they do have the same direction. But they do not have the same length. So these two vectors, or directed line segments, we cannot say they are equivalent. They are not equivalent directed line segments. They're not equivalent vectors, even though they both have the same direction, the same slope, but they did not have the same magnitude. This one was twice as strong, so to speak. Twice the magnitude of this one. So therefore, these two vectors, they are two vectors with the same direction, but they are not equal in magnitude or length. So therefore, all we can say is the two vectors have the same direction, but because they're not the same length, they cannot be considered equivalent vectors, or equivalent directed line segments. Thus, vector u is not equal or equivalent to vector v, and vice versa. They're not equivalent to each other. However, note, vector v is equal to vector u times 2. If you doubled the magnitude of vector u, they already have the same direction. And so if you doubled the magnitude of the smaller vector u, doubled it, well then that vector 2 times u, this is now a new vector, double the length of vector u. So when you double the length, you still keep the same direction. It's just now you doubled the length, and so then the vector 2 times u, which is a new vector, it's just double this vector. And then you could say that the vector 2 times u is equivalent to vector v, because they already had the same direction, and now when you multiply this by 2, they will have the same magnitude or the same length, and then you could say that they would be equivalent or equal vectors. And you might say, well, how can they be equal if they don't have the same initial point and the same end point? The neat thing about vectors, because they represent a force, so let's pretend a person gets up and they measure, they say, push as hard as you can against the wall. Or some object. And it might move. If it's a wall, it's not going to move, I don't think. And then they measure that force, and you had to push that on that object in a certain direction. And then someone else comes there, and if they pushed with the same force in the same direction as you did, but they moved the object, maybe it was a carnival, and then they had to move the tent or something, and now someone else came and played, and they pushed on the same game, whatever, I'm just making this up, of course, and now they push on it with the same force in the same direction you did, except now that the tent moved. But so your initial point and terminal point is not the same as their initial point and terminal point. But since they have the same direction and they have the same magnitude or length, then we would be able to call them equivalent vectors or equivalent forces. So, okay. So in terms of WebAssign, we needed to put the magnitude and slope. Well, this slope was 6/10, but we reduced it down to 3/5. And this was double the first magnitude, which was double the square root of 34. Let's check those answers. And they didn't want to grade it, or I missed it. I must have not clicked it. So they're all correct. That's good. Now interpret your results. Because they have the same slope, we know they have the same direction. So let's see. Do any of these say have the same direction? Do not have the same magnitude or direction. That's not it. They have the same direction, but they do not have the same magnitude. That's what happened, isn't it? So they are not equivalent. So this is true. What about this one? U and V have the same magnitude. You don't even have to read anymore because that's not true. U and V have the same magnitude. So this is the only one. U and V have the same direction, but not the same magnitude. So they are not equivalent. So this is all true. And we are good. Okay, so hope that made sense so far in our introduction to discussing directed line segments, vectors. Let's go on. Next, I would like to help with number 10. By the way, number 7 is virtually the same. It's the same exact question, just different two. Vector u are this first directed line segment and this directed line. They're just two different ones is all. But otherwise, the question is the same. So that's for you. Number 10. They give us an initial point. We'll call it P again. The terminal point, we'll call it Q again. And then we're going to draw the vector V, or the directed line segment PQ. And then we'll answer the question. One of which is find the magnitude, which we've already been practicing. So here we go. So let's go to my notebook here. And number 10. Okay. So let's see here. Number 10. Given the initial point, and I took the liberty of putting the letter P there, -5, -1. And terminal point, I took the liberty again. Oh, I didn't actually. I wanted to. I did below, but where is it? So Q. -13 and 5. So this will be, because it's a terminal point, we're calling it Q, and then therefore this is the second x value, the second y value, and this is the first x and y value. So now here is the graph. Here's the origin. X-axis, y-axis, our two-dimensional coordinate plane. All of this is the plane. Here is the initial point P. From the origin, you move in the x direction 5 units to the left, or we say -5. In the y direction, we move 1 unit, a -1 unit, which is 1 unit downward parallel to the y-axis, downward. And so here is the initial point P of our directed line segment, -5, -1. And now the terminal point is -13, 5. From the origin, x being -13 is leftward. This is just a sketch. 13, upward 5, and I didn't do that so well. It should have been like right here. But this is zoomed in, so it makes my error look a lot worse than it does. It's still okay. I can see it on my own paper too. Okay. I should have had it right here. Sorry. So I just can't live with that. So we're going to have to erase it, huh? So it should have been a little bit shorter. So here's 13. So right here. Okay. Phew. Now I can breathe better. Okay. So here is our point. Oops. Point Q. -13, 5. Point P, -5, -1. Okay. So 1 is find the magnitude. One of the questions is find the magnitude of this directed line segment PQ, or they call it vector V. Vector V. Got to turn your head sideways a little bit. That's a V, vector V. Well, to get this magnitude, we use the distance formula again, which, did I write it down somewhere? I guess I didn't. But what I did do is, so I kind of did it when I wrote this out, but remember the distance formula is x2 minus x1, quantity squared, plus y2 minus y1, quantity squared, and then all inside a square root. So from our formula here, square root of x sub 2 minus x sub 1 squared plus y sub 2 minus y sub 1 squared. So if we do that here, so the magnitude of vector v, I just didn't write the first step for some reason, I don't know why. The square root of, so what is our y sub 2? That's this 5. I'm so sorry, x sub 2, which is negative 13, minus x sub 1, which is negative 5, and that's squared, plus y sub 2, which is the 5, minus y sub 1, which is the negative 1, right here, negative 1. So minus a negative 1 squared. And so negative 13 minus a negative 5 is negative 13 plus 5. Negative 13 plus 5 is negative 8. So it's going to be negative 8 squared. Negative 8 and then squared. So that's right here. The square root of negative 8 squared plus y2 minus y1. 5 minus negative 1. 5 plus 1 is 6, so 6 squared. So I have that right here. And the real reason why I didn't write this is because in a moment we're going to do this, well, I don't want to say it yet. It's not the right moment. So, but notice right here, there's this x2 minus x1, and that's exactly what is up here. Anyway, let's hold on up that. Sorry. Okay, let's finish the magnitude. So we're right at this point. Well, negative 8 squared, negative 8 times negative 8 is positive 64. 6 times 6 is 36, so 64 plus 36 is 100, and the square of 100 is 10. So this magnitude from initial point P to terminal point Q, the magnitude of the directed line segment PQ, or we say the magnitude of the length of vector V is right here is the 10 units. 10 units. So that's right here. Okay, very good. Next, what I'd like to show you in our continued discussion of introduction to vectors is the following. Remember I was saying before, you were at the carnival and you played this game where you had to push on whatever the game was, and it forces you to push in the same direction all the time. And your force was whatever number. And pretend 175 pounds. And someone else played the next day, but they had moved the tent. But the machine is still facing the same way, and you still have to push in the same direction. So your directions are the same, and that person's force was also 175 or whatever I just made up. So your forces were the same. And so what I'm trying to say, maybe not very well, is when we have a directed line segment with initial point and terminal point, if we moved it anywhere up here, anywhere, as long as we have the same run and the same rise. So let's see, this was from here, this way was -8, and from here upward was 6 units. That's what we have right here. That's what we did up here. So just pretend if we started right here, now I'm going to mess up my picture, but if we started, say, right here, and I'm not going to be able to draw it very well, but just pretending, if we went -8, -8 units, and then up 6, and I just drew it freehand, as you can see. Now connect from initial to terminal. Well, that directed line segment, I didn't do a great job, but hope you get the idea. It's the same direction as this one, because this one was moved 8 horizontally to the left and upward 6, and now connect it. And if you do the same thing anywhere on this plane, well, then you're still going to move 8 to the left and up 6, and then if you connect it with a directed line segment or a vector, well, then this vector here and this vector here are equivalent, because they have the same direction and the same length. So this vector can be picked up and moved anywhere we want. So this directed line segment is equal to this directed line segment. If you pick up this directed line segment and you move it over here, as long as if you now move 8 units leftward, 6 units upward, draw from initial to terminal, then this directed line segment is equal to this directed line segment, which is equivalent to this directed line segment, even though I'm just sketching. Earlier in this lecture video, I told you about there's a slight distinction between directed line segment and vectors. I wasn't sure if I was going to say what it is, but I guess this is a nice moment, so because of what we're talking about. So to be really formal about everything, and it really doesn't make that big of a difference, but this directed line segment, you can move the initial point, as I just mentioned, anywhere you want on this entire coordinate plane, and then create an equivalent directed line segment by simply picking a point somewhere, move 8 units to the left, upward 6, and connect it. And now you have another directed line segment that's equivalent to this one. And so there's an infinite amount. There is an infinite amount of those equivalent directed line segments of this type, or of any type, but just say this one for the moment. An infinite amount, because all you need is to start at a point, and there's an infinite amount of points on this coordinate plane. So wherever you decide to start, who knows, where the heck, 5,000 miles away somewhere, and then you draw initial point, and then 8 units over and 6 units up. Well, now you have another directed line segment that has the same direction and the same magnitude as this one, and the same as this one, and the same as this one. So there's an infinite amount of those equivalent directed line segments. Now, it's very useful in mathematics, especially when we get to calculus 3, and we want to start talking about functions and forces in 3 dimensions instead versus only 2. And then the algebraic properties and trigonometric and calculus properties of vectors tend to be friendlier than if we just stick to only real coordinate points. I don't know if I said that perfectly well, but anyway, there's an advantage to having things in vector form. Advantages. Not always, but but there are certainly many instances where there is. So, okay. So now, if we take this whole entire collection, infinitely many collection of equivalent directed line segments, where you have an initial point and you move left, horizontally left 8 units and then up vertically 6 units and draw your directed line segment, if we decide to move this initial point and put it right at the origin, it becomes very useful when we start to want to put an angle in there for the direction of the vector or the direction of the line segment. So that's what they're going to ask us to do, and also just to identify what the direction of the directed line segment is, or what is the. It's easier to visualize instead of, I mean, if you had a vector way out here, 5,000 miles out, we don't want to put it over here. We'd like to bring it in and with the initial point at the origin, and then keep the same direction, move 8 units left and 6 units up and draw it. And now you have the vector that represents all of these infinitely many directed line segments. So we don't really need that definition, really, but that's what they typically say. The vector, where you move the initial point of a directed line segment, move it to the origin, and then move it the same way that the directed line segment moved. In this case, 8 units left, 6 units up. Now draw that from initial to terminal. And now that is called the vector that represents this directed line segment, this directed line segment, this one, all of them. Anyway, so we will, whether we want to get carried away with that little slight, it's a little slight distinction, but it's nothing to worry about. I think someone could even argue against that definition. But anyway, they will ask us to do this. Move this directed line segment into standard position. Standardize it. Take wherever it began, and then the heck with it. Put it right here. Put it right here at the origin. And now write down that vector. And what is it? How is it going to be defined? Well, 8 units to the left and 6 units up. That's how it's going to be defined. So look down here. It's the sketch of vector PQ, this one, or vector V, I should have written here, or vector V in standard position, which means the initial point is at the origin, where the x and y axes meet, the origin, 0, 0. Now move in the same direction as the directed line segment it came from, which is move 8 units to the left and 6 units up. 8 units to the left and 6 units up, and there is the terminal point. Connect the initial point to the terminal point, and here is the vector V that represents this directed line segment, this directed line segment, this one, and this one, and this one, that are all the same. And we call this vector now the vector that's put in standard position. So they might give us a vector that's already in standard position. They might just give it to us. Or they might give us an initial point and a terminal point in which the initial point does not begin at the origin, and then we just have to, they'll ask us to write it. They might ask us, the most obvious thing is to say, write this directed line segment, but in standard position. Or write this vector in standard position. Or they might say, there's several ways to word it. They might say, take this directed line segment and rewrite it in component form. The components are the amount of horizontal movement we make, -8, and the amount of vertical movement we make, which is 6 units up, +6. And in component form, I have it written up here as well, but in component form, you write vector v. I'm writing with my other hand here, okay? And this is the notation for component form. It's supposed to look the same. And you put the horizontal movement first and the vertical movement second with a comma. And so what was that? You move 8 units horizontally to the left, so -8. And then 6 units upward, which is +6. So here is what's called the component form of a vector or a directed line segment. In this case, the directed line segment PQ, which also you can call a vector. But move it now, as soon as they say put it in component form, that means you're moving it where the initial point is at the origin. The terminal point is such a place that does not change the direction of where it came from. And the direction of where it came from was to move from initial point horizontally 8 units to the left, -8 horizontal units and 6 vertical units. So then that's what you write. That's component form. The horizontal component and the vertical component. And we have to understand, well, that means, where do I start? Well, that's just it. When it's in component form, that means you're starting at the origin. If you start at any other point, well, then you would say, okay, I want to start right here, and I'm going to move -8 horizontal units and 6 vertical units, and there is an equivalent vector or an equivalent directed line segment. But again, I'm not trying to make things difficult, but authors will say that the set of all equivalent directed line segments, the vector is the one that you put in standard position is the one vector that represents the infinitely many equivalent directed line segments. But it's not a big deal, so you don't even have to worry about that. Okay. So, what the heck was the darn question? Given initial point, -5, -1, terminal point, -13, 5. Seems like it's been a long time already, huh? Sorry. But I'm using these first two problems to introduce virtually, not quite everything, but a lot of it. And so, find the magnitude of this vector, which we did, which was 10 units. By the way, the vector now that we moved and put it in standard position, it's still going to be, the magnitude's still going to be 10 units because it's still 8 units left and 6 units upward. So you'd still get this with your distance formula between the initial point and the terminal point. You would still get 10 units for the magnitude. Of course, because we're not changing it. It still has the same direction as directed line segment PQ, and it still has the same magnitude, the same length. So they are equivalent, yeah? Okay, so then the other question was to write this vector now in component form, which means how much is the movement? You can think of it in two ways. what is from the initial point to the terminal point, what is the horizontal movement component value? -8. What's the vertical component value? That's 6. More importantly is, if you now move this initial point P to the origin, now where is described that directed line segment, but have it moved to the initial point being the origin? And that would be then, the only way you could describe it now is to say, well, from here you move -8 units and then up 6, and now those are this is your horizontal component movement value, and this is your vertical component or your vertical movement value, 6 units. So now up here, I said I wanted to wait on this, but now we're ready. So now this will make more sense, I hope. So the directed line segment PQ or vector V is in component form. All you have to do is to figure out the horizontal movement is to do what we did up here on the distance formula, which is to take x2 minus x1, comma, y2 minus y1. Not to get the magnitude, just to get the component form. And so this part right here is the same as this part right here, which is the same part as this part right here in the distance formula. X sub 2 minus x sub 1, y sub 2 minus y sub 1, except here we're not squaring it and putting it in a square root and adding it because we're not getting the distance. We're just writing it as an in component form. So what would that be then? What's our x sub 2? What's our x sub 2? It's the -13 minus, what's our x sub 1? -5, just like we wrote right here. And that's the real reason why I didn't write it down here, and I kind of forgot that I maybe should show you. And then comma, y sub 2, 5 minus y sub 1, which is -1. So 5 minus -1, which is exactly what we wrote right here when we computed the distance, the magnitude. And just like it was here, this became -13 plus 5, which became -8 squared. Well, this just becomes -13 plus 5, -8, and that is our horizontal component, -8. And 5 minus -1 is 5 plus 1, which is the 6, which is the same thing we had right here, which was right here. And we put it right here, but we don't put squared or anything, because this is just now this is the directed line segment PQ, or the vector V, in component form. And I would like you to think of it as when we then move the initial point to the origin. And this is a way to describe this directed line segment. I mean, you can say this, oh yeah, okay, another way of saying it is, okay, this is the component form of the vector, or the directed line segment PQ, where P is where you start, initial point. Then from -5, you would move 8 units to the left, 8 units to the left, and then from the y value of -1 on the initial point, right here, down 1, I just move over here. And now I'll move up the vertical component, which is 6, and that gets you to the terminal point of the original directed line segment PQ. More importantly, though, well, I don't know if it's more important, but you also need to know that if we do move this and we write it in component form, then we are placing the initial point right here. And then 8 units to the left, up 6, and then you would draw it, which is what I've already said like 5 times at least, okay? Which is right here. Okay, so the horizontal component of vector V is -8 horizontal units, or movement. That's the first number in this funny symbol notation, which is component form. And the vertical component of vector V is 6 vertical unit movement. So we're done for this problem. except to type it in. But I want to use this problem to teach you one other way of writing this, a vector in where you move the initial point to the origin. But first, let's write our answer in here. How are we going to get this funny symbol? This funny component symbol. It's like a less than, a greater than kind of thing. But with WebAssign, you come over here to the CalcPad toolbox, or whatever they call it, and you click Vectors, and then we're going to use this one right here. They call them vector brackets, vector grouping symbol, open vector, close vector symbol, open vector bracket, close vector bracket symbol. You click it. Of course, I had to be here already. Let me erase it. Ow. If you're out here and you click it, well, I can't even get to the toolbox. You got to be inside first. Click Vectors. Click this one. And -8 was the horizontal component value, of course, and 6 is the vertical. And check. And so there we go. I would like to show you one other form yet, which is on this assignment, but I think it's the best moment, or it's a nice moment. I don't know about best, but it's certainly a nice moment to show you. So, right here, there is an alternate form of writing a vector, and when you put it in standard position, other than the component form, which is what we just put, -8, 6. How do we do this alternate form? It's very simple. Each horizontal and vertical unit can be labeled or designated or called or thought of as a horizontal vector. So like from right here, if you move 1 unit left or 1 unit right, that's a movement in the horizontal direction. And we can call 1 unit a vector. And vector I is the letter they used. Who knows what reason? They just select letters. Vector I is the amount, which is equivalent to 1 unit. If it's 1i, that would be positive. That would be 1 unit rightward. So the vector I would be like that. If that's 1 unit, pretend. And that would be vector I. If it was negative, like from here to here, it would be -1 unit, a second one, a third one, a fourth one, a fifth one. Each one could be called as the I unit vector, and you could write it as -5i. That much. If you move 1 unit upward or 1 unit downward in this direction, parallel to the y-axis, then they call that each unit, if you write it as a vector, 1 unit, instead of calling it I, you call it j. So from here, 1 unit upward would be a little tiny vector that's only has magnitude length 1 unit, but now it's the second dimension movement, the vertical, and that would be called j. So this would be 1j. From here up to here would be 6 units. And this would be 1j, 2j, 3j, 4j, 5j, 6j. This way would be -1i, -2i, 3i, -4i, -5i, -6i, -7i, -8i. So how can we rewrite a vector that's in standard position other than component form? You can write it as of movement in the horizontal direction and the vertical direction using these little tiny unit vectors I and j's. And that's what I'm saying here. There's an alternate form of writing a vector in standard position other than the component form, -8, 6. Each horizontal unit can be labeled as a horizontal vector I. Each vertical unit can be labeled as a vertical vector j. A vector in standard position can be written using these unit vectors I and j relative to the number of these linear, you're moving in a linear fashion, linear, not slanted. Well, I mean, this is still a line, but we're moving, we're not moving in a curved amount, but anyway. So, can be written using these unit vectors I and j relative to the number of these linear unit vectors we must move from the origin to the terminal point of the vector. Therefore, our vector v, which came from the directed line segment PQ, P had this initial point, Q this terminal point, and then we moved it into standard position, and we know it's -8 horizontal units and then 6 vertical units. So here's the component form, -8, 6. If you like to write it in an alternate way, in terms of the number of horizontal unit vectors I and the vertical unit vector j, vectors j, then we could say, okay, from the origin you're going to move -1i, -2i, -3i, -4i, blah, 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 -8i, plus 1j, 2, 3, 4, 5, 6j. So, vector v can be written as a linear combination of unit vectors I and j, and we can say that vector v is equal to -8i plus 6 of -8i of those horizontal unit vector. Each one of them is called I, so it's -8 of those unit vector i's, plus the vertical movement up to the terminal point is one of those unit vector j's plus another one, a third one, a fourth, a fifth, a sixth one. So plus 6 of those unit vector j's. Well, I hope that makes sense. Okay. All right, class. So next I would like for us to talk about number 9 together. So they say, find the component form and the magnitude of vector v, where here is the sketch of vector v. They could have also said the directed line segment PQ. You notice this arrow means that's the terminal point of the directed line segment, or the terminal point of our vector v. Then therefore this must be the initial point of the directed line segment, and we could put a P right here and a Q right there. They didn't bother to do so because there's those two ways to label it. You can label it as the directed line segment PQ, or just say that I don't want to say that, I just want to say vector v. But then we have to realize that, oh, here's the arrow, that's the terminal point, and this is the initial point. So we're going to compute the magnitude, or which is the length. Now notice, because this is a vertical, you don't have to use the distance formula if you don't want to. You could just count, because it's just the distance is from -5 up to 8, so you could just do that mentally if you like. So from -5 to right here is 5 units, and then from here to here is 8 more units. So 5 units plus 8 more are 13. So that's going to be the length of this directed line segment, or this vector, 13 units. Or we can also use the distance formula between 2 points. This will be our x sub 2, y sub 2. This will be our x sub 1, y sub 1. So you can do it either way, and we should get the same answer, of course. I did write it down in my notebook for your benefit as a P and a Q, and then use the distance formula. Okay. So let's do that. So number 9, here is the, as I mentioned, I labeled it as initial point P, terminal point Q, which is 8, 8, and initial point 8, -5. Here's the x-axis, the y-axis, and here is the directed line segment PQ, or we can also call it, as the author did, just say vector V. If they call it vector V only, and you would like to label it as P initial point, Q as terminal point, well then please do so. Nothing wrong with it. It's equivalent. So it's perfectly fine if it helps us to get whatever we're being asked to do. When one is to find the magnitude, which we said should be 13. But let's show you with the distance formula. So the magnitude of a vector or directed line segment using the distance formula right here will be square root, of course. Call this one x sub 2, y sub 2, and x sub 1, y sub 1, as I already mentioned on the WebAssign page. So x sub 2 is 8. X sub 1 is also 8 because this is a vertical line and the x values are the same. It's the same distance over. It's 8 units over. Whether we're right here, it's 8 units over, or whether we're up here at the top, it's 8 units over. So 8 minus 8, 8 minus 8 is your x sub 2 minus your x sub 1, and of course that's going to be 0, so 0 squared. Which is why you didn't really have to do this part, and you could just count. Plus, though, your y2 minus your y1, which is, y2 is this, which is 8, minus y1 is this one here, -5. So 8 minus -5. Quantity squared. Well, minus a negative, subtracting a negative turns into a positive, so 8 plus 5 is 13. And so there's your 13 squared. 0 squared plus 13 squared is still, that just doesn't do anything to the 13 squared. So you still have 13 squared. You could write here 169 and then take the square root of 169 and get right back to 13. Or you can just realize, oh, I have a square powering of power 2 value, and it's inside a root 2. And they are inverses of each other, so they compose out to just whatever this is, the base is, which is a 13. So either way, you're going to get 13. So I hope that makes sense. So that's one answer that they were asking for, the magnitude. And now what else do they ask for? What the heck is this? Component form. Component form. So what's that again? That's when we move this initial point and place it on the origin and draw the same directed line segment now, but just that we've changed the initial point and the terminal point, but it's still in the same direction as it was to begin with. So this was vertically upward to the terminal point. So this will start right here and go vertically upward to its terminal point. So we could have drawn that on the same grid, the same coordinate axes, I just didn't, just to try to not confuse anyone unnecessarily. So here is a new coordinate system. x and y axes. And sorry, my dogs were going to come in through the pet door, and now they changed their mind. So I might have scared them off talking all about this vector stuff. They shy away when I talk about vectors. Now trigonometry, they like it. They come and sit down, and look at me, and they seem very much interested. But vectors, no. I don't understand. Anyway, can't understand everyone in this world. Okay, so let's go on. Yeah, so we move this vector PQ, and we move it in so that the initial point is at the origin, and then, well, you draw it with the same direction, which was vertically upward, and we know the length is 13, so I just made a sketch. And so this vector is the representation of directed line segment PQ, or vector V, but in standard position, simply moving the initial point to the origin and then draw the same directed line segment or vector. So that's what that is. Now, how can we write this? Well, in component form is one way. We could also write, oh, there's a new point here as the initial 0, 0, and the new terminal point would be 0, 13. And then we could have directed line segment, a new one, PQ. But that's not what they want us to do. They want us to write in component form now means having moved directed line segment PQ, as I just told you. Now, what is the horizontal movement and the vertical movement from initial point at the origin to terminal point? Well, do we move leftward or rightward at all? No. So there is no horizontal movement. There is no horizontal movement. So we don't leave it blank. We represent by 0, of course. And then the vertical movement is upward, positive 13 units. And therefore, in component form, vector V now can be written as 0, 13. Now that was easy to see because it was vertical. You can also do this. Use this formula to put a directed line segment or a vector and place it into standard position, and to do that, to get the horizontal component value, the vertical component value, you do the same thing we did with the distance formula. You say x sub 2 minus x sub 1, that gives you the difference in the x values, which would be the horizontal component movement amount, and then y2 minus y1 would give you the difference vertically. And that's exactly what we need to do when we use the distance formula, but then we continue by squaring them to get the length or the magnitude. But just for component form, all we want is that amount of horizontal movement, the amount of vertical movement. The horizontal movement is 0. From here to here or down here. From here this way there is no horizontal movement. That's because 8 minus 8 is 0. What's the vertical movement? The vertical component? It's 8 minus negative 5 from here down to here, which is 8 plus 5, which is 13. And so here is the component form of this directed line segment PQ, or of this vector V, which means now you can consider it as the initial point is at the origin. And this gives you then, not only does it tell you the horizontal movement and the vertical movement, but it tells you the end point, the terminal point of the vector when it's in standard position, because it's going to have to be 0, 13. Right here, this point is 0, 13. How else can we write this vector that is now in standard position? How else? Well, we can write it in terms of from the origin write down how many horizontal I unit vectors you move and how many j vertical j, how many vertical unit j, if I can say it correctly, how many vertical units, or we say unit vector j, how many are there from the initial point to the terminal point, how many vertical units and how many horizontal, but written in terms of I and j, unit vectors. Well, you just do the same thing. You say, well, there is no movement horizontally, so that's vector v can be written as 0i plus 1, 2, 3, 4 of these, 1j, 2j, 3j, 4j, 5j, up to 13j. So 0i plus 13j is the way we can write this vector v as a linear combination of unit vectors I and j. Like, why am I showing you this? I know they didn't ask us yet, but I think it's better to show it to you now than when we get to the end and you're like, well, because now I think it all kind of fits together nicely now. Well, at least I hope so. Either way. So we come up here. What do they ask for? The vector in component form. They could have said as a linear combination of I and j's, and then we would have written 0i. I wonder what happened if I write that. Just out of curiosity. By the way, you go to vectors for linear combination of I and j, and you write 0. You got to use this I. If you use the I on your keyboard, most of the time it marks them wrong, but every once in a while I've noticed it marks them correct. I don't know if that's just a programming slip-up from the WebAssign people or what, but most of the time they're wrong. So you got to use specifically this bold-faced I, which represents a 1 horizontal unit vector. So 0i plus 13j. I don't know if it's going to mark it right or wrong. I mean, it's not, we're writing it not in component form, but as a linear combination of i's and j's. As you move on past this class and into other math courses, they kind of start to mesh the terminology together, and they kind of say it's the same thing really, so they don't get very picky anymore. And so I don't know what they're going to do right now. They might mark it correct or not. I don't know. But we'll find out. So they do mark it correct. That was my suspicion. But for the moment, we are really supposed to write this symbol, open vector bracket 0, 13, and have it graded for us, and we should be good. Okay. So I hope that makes sense, everyone. So next, I want us to look at number 16. So let's see what that has to say. Find a unit vector u. Now they didn't say write a vector as a linear combination of unit vectors I and j. That's not what they're saying. They're saying come up with a vector called u, doesn't matter the name, that can only be, if it's a unit vector, that means the magnitude can be 1 unit long. So it's a little short vector whose magnitude is 1 unit. Notice right here, magnitude is, or length is 1 unit. But it has to have the same direction as this vector, v. So the same direction as vector v. Here's vector v. Notice it's written right here, and I don't see a point, initial point and a terminal point here. I just see this open vector bracket, close vector bracket, which means this vector v is not written with initial point p and terminal point q. It's written in component form, which means, I hope we agree, it means the initial point has been moved to the origin. And then we move, horizontal component is 4 units to the right. The vertical component is -3, that's 3 units down. And that'll be the terminal point, and the origin is the initial point. Now connect the initial point from the origin to the terminal point, and there's your vector v. Okay, so let's do that. So, number 16, given vector v in component form 4, -3, or as a reminder, we could have written it as a linear combination of horizontal unit vectors I and vertical unit vectors j. So that would be from the origin, it would be 1i plus 2i's, 3i, 4i, and then vertically downward, so -1j, -2j, -3j. So it would be 4. I mean, I hope you realize it's saying the same thing as component. This is says, hey, start from the origin, horizontally move +4. 1, 2, 3, 4. This is saying, hey, start at the origin and move 4 of those unit vector, those I unit vectors. Those I are each one of them. I is a single unit vector in the horizontal direction. So 1i, 2i, 3i, 4i. So 4i is another way of saying a horizontal movement of 4. Except you're just writing them as a little tiny vector plus another little tiny vector plus another little tiny vector plus another one. 4 of them. And minus one of those little tiny vertical vectors j, but downward, minus another one, a second one, minus the third one, -3j. 3 of those j vertically unit vectors. Well, either way, you end up right here. And we're at the terminal point, which is 4, -3. You can think of this as the p, x, 0, 0, and this says q, your directed line segment PQ, but where p, the initial point, is at the origin, which means it's in standard position. So whenever they give it to us like this, in component form, or like this, as a linear combination of I and j, that means we have to realize that means it's the vectors in standard position. We start at the origin, and then we read either the component form or the linear combination of I and j form to figure out where the terminal point is, to figure out how to move horizontally, how much to move vertically, and then that gets us to the terminal point of our vector. So now, what the heck was the question? Find a vector u that's in the same direction of vector v, same direction, and they don't tell us here. They don't tell us how to write it, but we could write it in component form, or we could write it as a linear combination of I and j's, either way. So now we want a vector u that's in the same direction. That means it's going to start at the origin as well, and it's going to move right on this same direction, this same pathway as vector v. But it can only be, it's going to be a unit vector. That doesn't mean I, or doesn't mean j, because that I is only horizontal movements, left or right. J vectors are only unit vectors, yes, but they're only upward or downward 1 unit at a time. A slanted 1 unit vector is not I or j. It's neither one. It's just a vector that has magnitude 1 that's in the direction of, well, in this case, it's the same direction as this vector v. So what we want, everyone, is a vector u that starts right here and ends right here. Pretend that's 1 unit. So what we want is our vector u that's in the same direction as vector v starts at the origin and only goes 1 unit. And so this tiny little vector right here, that's what they want. What would that be? What's this vector right here? And we're going to call it vector, unit vector v. There's nothing magical about calling it v. It can be called anything. But unit vector v. That's in the same direction as, unit vector u, pardon me. That's in the same direction as vector v. Well, all we have to do then, class, is first find out how long is this vector v. How long is it? What's the magnitude? And when we do that, well, let's do that first. Well, this is kind of a common, if it's 4 units over and 3 units down, that forms a very familiar right triangle. 4 over, 3 down, then this, I can consider this length here the length of a hypotenuse. So it's going to be 4, 3, and 5. Or we can use the distance formula, which I wrote down. The magnitude of vector v, this vector v, from the origin right to here, this terminal point, is the square root again of x sub 2 minus x sub 1 squared plus, so 4 minus 0 squared plus negative 3 minus 0 squared. 4 minus 0 is 4, 4 squared. Negative 3 minus 0 is negative 3 squared. 4 squared is 16. Negative 3 squared is 9. 16 plus 9 is 25. And the square root of 25 is 5, which is what we expected. So from here to here is 5 units. Okay. Vector v, it's in this direction, and it's 5 units long. Great. Well, what do they want? They want a vector that's the same direction as vector v, but it's only 1 unit long. Okay. So what we can do then is borrow vector v, because vector u is going to be, we're being told it has to be the same direction. Vector u here has to be the same direction as vector v. So we borrow vector v, which is this 4i minus 3j, which is from here to here, which is 5 units long, and simply divide it by 5, divided by the length, its length. So if you divide this up into 5 equal pieces, 1, 2, 3, 4, 5, we want the first one from here to here. That's what they want us, and we're going to call that, and that is 1/5 of vector v. 1/5 of it. Another way to say, well, here it is, 1/5. Or you can say divide vector v by 5. Divide it by its magnitude. And that'll give you a unit vector that's in the same direction as the vector, the original vector v is in. So therefore the unit vector, whatever they want to call it, in this case vector u, in the same direction of, I mean, you don't have to write it, because as soon as you say direction, that's what it means. But in the direction of vector v means the same direction of vector v is, well, you take vector v, divide it by its magnitude. So take vector v, which can be written in component form. You can leave it like that if you like. I just like it this way, 4i minus 3j, and then divided by 5. And now you take this term divided by 5, and then this term divided by 5. I think it just makes more sense to us when we're learning students and we're being introduced to these vectors and all this terminology and so forth. So now take 4i and divide it by 5, and take negative 3j and divide it by 5. And you get 4/5 I minus 3/5 j, which is from the origin you move not 4 units over and 3 units down, because that would be vector v. You move 4/5 of a unit over. That's not even one whole unit. 2, 3, 4. 4/5 of these I vectors. So 4/5 is less than 1. It's not even one unit, one of these I vectors. It's 4/5 of it. And then move down 3/5 of a vector, vertical unit vector, which we call j. 3/5 of a j vector, of the j vector. And then when you do that, you'll be right here on this same line as this vector v is. And there, that would be your unit vector u. That's in the same direction as vector v. And then we can leave it in we can leave it in the vector, and now this is all called vector u. You don't have to put a grouping symbol around it. Or if you want to write it in component form, then you write the horizontal component first, the horizontal movement from the origin, which is the 4/5, and then the vertical secondly. Lost it. Or I can't. Here we are. Horizontal component value and the vertical component value. 4/5, comma, negative 3/5. Okay, so we should be able to put either one of these in to WebAssign, because they don't even tell us how to write the answer. So just to be, I don't know, I'm going to put 4/5. Oops. I and then it was minus 3 divided by 5 in the j, and that's one way to write. Well, I hope if you get it right. And there's the nice green check mark. We could also decide to write it in component form, which would be then go to vectors, open vector bracket, and inside put the horizontal component value 4/5, comma, negative 3/5. And that also should be graded correctly. So I hope that makes sense, class. Okay, very good. So class, so that was 16. 15 is the same exact kind of problem. So that's for you. 17 is almost the same kind of. It's virtually the same, except they give us, it doesn't matter on the letters, okay, what the names are, but just think, okay, they give us a vector. Here's a vector. Who cares what the name it is? Don't even worry about the name right now. It's just, and it is in component form. So that means from the origin, in standard position, the vector is 7 units leftward horizontally, 24 is the vertical component, so upward 24, and then connect from the origin to that point, and that's the vector u. So let me show you that. We have a vector in component form, which means it's in standard position. Who cares what the name is? And from the origin, its horizontal component is -7. The vertical component is 24. And that's the terminal point. That's the terminal point. We could have written this as a linear combination of i's and j's, and we would have written -7i plus 24j. But perfectly fine like this. Now, we're supposed to find a new vector that's in the same direction. That's in the same direction as this first one. So the new vector is going to start here at the origin, and it's going to go in the same direction as vector u, as this first one. Don't get caught up in the names, because you might kind of confuse yourself from the previous problem. So who cares what the names are? You have this initial vector with in component form, -7, 24. So here it is. Now, come up with a new vector that's in the same direction as this first one. So it's going to start at the origin, and it's going to either be shorter, it might be 1 unit long like the last problem, or maybe it's going to be 2 units long, or 5 units long, or 20 units long. However long they want us to make it. How long do they want us to make it? Oh, the new vector, the magnitude of the new vector is supposed to be 75 units long. Okay. So it's going to start right here, go in the same direction as the first vector, but it needs to be 75 units long, so it's probably going to be longer than this one. Well, let's find out how long this one is. Let's find out how long it is. Maybe it's 75 units and we'll be done. If it's 75 units long, then it's a trick question. And then the vector they wanted us to find is the same as the vector they gave us, and that would be kind of nasty, but I doubt they're going to do that. Okay. How do we find how long this vector is? Well, that's the magnitude. So we have to use the distance formula. And here we are, x2, y2, -7, 24, and the origin 0, 0. So let's use the distance formula again. First find the magnitude of the first vector, whatever they called it, who cares, which is the square root x2 minus x1, -7 minus 0 squared, plus y2 minus y1, 24 minus 0 squared. Well, -7 minus 0 is -7, 24 minus 0 is 24, and you have them squared still. After a while, you start to realize, I'm sure you already do, that if the vector is already in standard position, then every single time the initial point is going to be 0, 0. And when you're asked to find the magnitude, when you're asked to find how long that vector is that's in standard position, you can keep writing this -7 minus 0 plus 24 minus 0 Or you can just say, I know this is going to be 0, and I know that's going to be 0 because it's in standard position. So I'm just going to jump to this part and skip the writing down this step and just write this. It's perfectly up to each one of us to decide if they want to do that or not. If it doesn't feel comfortable, it doesn't feel right in our mind, then don't do it. Just write this. If you feel comfortable with it and it doesn't throw any unnecessary confusion, you start to get dizzy and you start to feel faint, well then don't write it. Do this first. I'm just kidding. I'm not trying to figure out what to say. Well, anyway, we get negative 7 squared plus 24 squared. Now, negative 7 times negative 7 is 49. 24 times 24 happens to be 576. Add those together, we get 625. The square root of 625, that happens to be a perfect square. 625 happens to be 25 times 25. So we can take the square root of 625 and it's 25. So how long is this original vector? What is the magnitude of this original vector? It's 25 units long. It's 25 units long. And what do they want us to do? What do they want us to do? To come up with another vector that's in the same direction as this one, but not that's 25. Thought they were going to trick us. If they would have said 25, then they would have tricked us and we would have wrote the same vector down. Negative 7, 24. But they did not. How long is the new vector supposed to be? Not 25 units, but 75. So it's the same direction as this one, but don't stop here at 25 units. Go another 25 and then another 25. So it's going to be 3 times as long as this one. 3 times as long. Therefore, since vector v is to be in the direction, the same direction as vector u, and has length or magnitude 75 units, then the new vector v is 3 times the original vector. 3 times the original vector. So this is one way to get the answer then. Therefore, the new vector v is 3 times as long as the original vector, which in component form was this. So you can just multiply 3 times negative 7 and 3 times 24, and then 3 times negative 7 is negative 21. 3 times 24 is 72, and that's one way. Or you could change this to a linear combination of i's and j's and write negative 7i plus 24j if you like. Distribute times 3, make it 3 times longer, and you'll get 3 times negative 7i is negative 21i. 3 times 24j is 72j, and that's another way to write your answer. If we go to WebAssign, and we write either way, I'll put it in a component form this time. Open bracket, open vector bracket, negative 21, comma, 72. And hopefully we're correct. And there we go. So I hope that makes sense, everyone. So class, I have about 40 seconds and I want to mention this. There will be a part 2 video for the rest of this section. But as an alternative way to find this same vector, we could have done the following. Take the vector u, this one, divided by its magnitude, which was 25, and then take this magnitude, which is this, multiplied by 75. I'm going to have to cut it here. But this is the negative 7i plus 24j divided by the magnitude 25, and then multiply it by 75. So I'll let you see that, and I have to go. I'm back, and I'm going to go over 2 hours. Oh my gosh. Now I'm going to try something different. Maybe it'll save me some time. And I will continue with this past 2 hours. And then when I'm done, I have to break it into 2 pieces or 2 parts, a part 1 and a part 2. I never did it before, so I hope I don't mess it up. But that way, I don't have to stop this lecture video down, encode it, have the computer encode it, and then upload it to Blackboard, which takes like, you may not believe it, but it takes literally about 2 hours to do. And it's a long time. Now it's going to take even, well, if I split it, it'll still, it's going to take, anyway, I'm going to try that. So let's keep going. So slowing down, alternatively, we could have found this vector that's in the same direction as the first vector, which was this one right here, which was, again, don't know if this thing is in the way, this little rectangle here. I don't think so. But the original vector, negative 7, 24, that was our original vector. They called it vector u. It was 25 units long. And now they're asking us for vector v, which is in the same direction as this vector, but instead of being 25 units long, it's supposed to be 75 units long. We already did it one way, which was nice, only because 75 is 3 times as long as 25. Otherwise, we might have had a little trouble. You can still do it. You just have to be careful with your fractions. But another way to do it is this alternative way, which is a little safer, perhaps. First, divide, get this original vector and get it the unit vector, which means that write down the vector that's in the same direction as this one, but it's only 1 unit long. So that this little tiny unit vector, that would be in the same direction as vector, this vector right here, but it's only 1 unit long. So this would be a unit vector. A unit vector. That's okay. I paused it. So class, let's get this unit vector from vector u. So to do that, you just write down vector u either in component form or as a linear combination of i's and j's, your choice, and divide it by its magnitude, which is 25. And if you divide this into 25 equal parts, then we want the first one. And so you just take this vector, negative 7, comma 24, and then divide it by 25. Like a few minutes on the problem before, to get the unit vector. For this one, we divided the vector, this vector, which was 5 units long, and we took this vector 4, negative 3, and then we divided it by its own length, which is 5 units. You took the vector divided by its magnitude, which is divided by 5, and then that gave us the unit vector that's in the same direction as vector v. So we're going to do the same thing as an alternative way, which is probably a safer way to do it, because it may not be always so lucky where the original vector is 25 and the one they want is 3 times as long. But I mean, you can really do it this way. It just may not be so numerically friendly, times 3. It might be times 3/2 or something. but whatever. Or we can do it this way. First, break down this vector and get the unit vector of it. So take the vector and divide it by its own magnitude, its own length, which happened to be 25. We did it up here. So alternatively, we can find the vector by the new vector, the one that's 75 units long, by first writing down the unit vector of the first one, which is vector u, which will be vector u, which is the negative 7, 24, negative 7i plus 24j, and divided by its magnitude, vector u divided by its magnitude, which is the 25. So vector u divided by its magnitude is, and then once you get that, so this right here is this little unit vector, this little red one, and it's negative 7 over 25 plus 24 over 25, negative 7 over 25i plus 24 over 25j. So that's this right here. If you go negative 7/25 of a unit, which is very little, plus 24/25 j, that's almost 1 unit upward, and that'll get you to the tail, to the terminal point of this vector, which is sometimes, not sometimes, but they also call it the tail of the vector. Now once you have this unit vector is in the same direction as the vector u, except now it's only 1 unit long. And we want a brand new vector, they just called it whatever you want to call it, brand new vector, the great long vector, that's going to be 75 units, but it's in the same direction as vector u, which means it's also the same direction as this little unit vector. So just take this little unit vector now, which is only 1 unit long, and multiply it by however many units the big long one needs to be, which in this case is 75. So then take that unit vector and multiply it by 75, and that'll give us the new vector they want us to find. So now take this little unit vector, the red one here, and the new vector v is 75 times the red unit vector here. It's the unit vector from vector u, and 75 times negative 7 over 25i plus plus 75 times 24 over 25j. And of course, now you'll see the similarity to this other way we did. 75 times negative 7 over 25, you can divide this first. 75 divided by 25 is 3. So, or the new vector v is equal to 3 times the numerator, because 75 divided by 25 divides to 3, and now you're going to have 3 times this numerator, 3 times negative 7i, plus 75 again multiplied by this fraction, 24 over 25. 75 divided by 25 is 3. 3 times 24 now. 3 times 24j, unit vectors j. And realize that's the same thing we did up here. We realize that the new vector is going to be 3 times as long as this one, because remember this one was 25 units long, and our vector v, the new one, was supposed to be 75 units long in the same direction, 75 units long in the same direction as vector u. So then that's just a kind of a clever way to do it. You just take this original vector u and multiply it by 3. And that's what we did right here. The new vector is 3 times the original vector. 3 times negative 7, 24 in component form. or 3 times negative 7i plus 24j in linear combination of I unit vectors I and j form, either way, it ends up being the same thing if you would do it this way. Well, you can see. So 3 times negative 7i is negative 21i, 3 times 24j is 72j, and that's the same answer as I mentioned right here. Well, that was a better explanation, I hope, than when I tried to rush in 20 seconds. Okay, so, where am I? Where are we? We're right here. Negative 21, comma 72 is in component form, or we could have written it as negative 21i plus 72j. Either way. Okay, class, so I hope that makes sense. So let's look at 18 and 19, just the directions though. Either one, they're the same directions. You have an initial point, hope that sounds familiar, call it P. A terminal point, hope that sounds familiar, call it Q. Connect initial point P with terminal point Q and you get the directed line segment PQ. The directed line segment PQ, or you can say the vector with initial point and terminal point. Now, write that vector as a linear combination of the standard unit vectors I and j. So, I hope I've already prepped you for that. That's why, well, one of the reasons I knew it was coming and I thought it was a better time before than waiting all the way till now. Just my opinion. So, then first, just put this in, move this so that the initial point is at the origin, and then the terminal point will be somewhere else. And how do you do that? Just to get it in component form, remember you say x2 minus x1, y2 minus y1, and then that gives you the horizontal component value and the vertical component value, but then write it with i's and j's instead. So that should be fairly simple and a very short 2 questions there. So I hope that's okay. It's just like way up here at the beginning. We had initial point and terminal point, and then they didn't ask us to write down the vector, but we well, here's one. Initial point and the terminal point, they wanted us to find then the this vector but in component form and then its magnitude in the component form, and that's when we did the x2 minus x1 and we got the negative 8, remember. We got the y2 minus the y1 and we got the 6, remember. And I think this was the problem. Then I taught you the not only the component form but the linear combination form. So then this would just become negative 8i plus 6j, done, without the open and close vector bracket symbols. Okay, so that's how you will do those 2 down here. 18 and 19. Next, I would like to do number 22 with you. 22. So they start out giving us a vector. Up and look at what is this in? What the heck is this? Negative 7i plus 18j. What the heck is that? Oh, that's the linear combination form of a vector that's in standard position, which means the initial point is at the origin, and then you move 7 horizontal unit vectors, or I vectors, 7 of them to the left, and then you're going to move 18 vertical unit vectors, which are called J vectors. Positive would be upward, 18 of them, and that'll give you the the terminal point or the tail of the vector. And once you have that, now find the magnitude, which we've been doing throughout all this lecture. And then there's something new here. We've talked about the direction before. At the very beginning of the lecture video, I told you they asked us for the slope. The slope, and I told you that was one way to describe the direction. The direction of the vector or of the directed line segment. But then I said the other way is to describe the direction of the vector in terms of its angle, in terms of its angle from standard position to the vector. And so that's what we're going to do right now. So, and that's 22. So, let negative 7i plus 18j. Exercise 22, given the vector v, which is negative 7i plus 18j. So I tried to draw it here. And I don't know how these little marks got here. I think from being on the other side of the paper. And now it's on this black part. And there's some pencils still. I gotta wash this, I guess, again. I'm sure you wanted to know all that. I don't have anybody to talk to here, except for the microphone. Be nice if I could have met you guys, but oh well. Speaking of which, if you mention to me in an email that I didn't get to meet you guys, and I wish I could have, then I will give you 1 point extra. It's not much, but if you want it on your test, it can be. It doesn't matter which test, numerically speaking. So whichever, say this chapter or chapter 5 test, so that way you can see it right away. Just email me and tell me that I mentioned it would have been nice that if I could have met you all. And that way you get a 1 point extra credit, which won't do much, but anyway, also it helps me understand if anyone actually is listening to my videos. And I hope so, but I don't know. Alright, so if you want to do that, you're welcome to do so. I would appreciate it, by the way. Okay, so here is the set of axes. From the origin move, this is written in standard position because it's not in component form, but it's in linear combination of unit vectors I and j form. Horizontal unit vectors I, vertical unit vectors j. So you move negative 7 of those I vectors leftward, 18 of those vertical unit vector j's to get to the terminal point of the vector v. And so now draw it, and here's vector v. Nothing different. Now find the magnitude. Okay. So the magnitude or the length of vector v is equal to the square root of, well, we could put 0, 0 again. We could put, I mentioned this on the last problem, after a while you start to just say, I don't have to keep writing the 0, 0 because I know what's going to happen. But whatever you like in terms of your comfort level, this point up here was, say it's point Q, and it's negative 7, comma 24. And this would be your second x value, your second y value, and this would be your first one, and this could be point P. Okay. Then the magnitude of vector v would be the square root of x2 minus x1, negative 7 minus 0, but negative 7 minus 0 will just be negative 7. And I didn't write down the minus 0 this time, not to be rude, but I'm explaining it to you, so. And then square. Plus y2 minus, oh, I think I wrote the wrong number down. I don't know where I got a 24 from. It was an 18, so sorry. I don't know where, I guess there's a 24 here. I don't know where I got it from. It's a mystery. Anyway, y2 minus y1. So 18 minus 0. Well, that would be 18 minus 0 inside, which then would just become 18. So I hope that's okay. Now, negative 7 squared is 49. 18 times 18 is 324. Add those together, and we get 373. The square root of 373. This is not a perfect square. So we leave it like this, square root of 373 units. So that goes right here. I think on this one I actually put this in here already. And that's good news. Yeah, I put it in already because here's the angle, which I'm not supposed to see yet. Now, the direction angle is what we're supposed to find next. So that's something new, or at least slightly new. The math is not new, but the terminology in describing it is new. So, another way to describe the direction of this vector that's in standard, that's the reason we want to put it in standard position, is so that we can describe the direction of a vector not only by the slope, which would be rise over run 18 divided by negative 7. That's the slope of this vector. Another way to describe the direction of this vector that's when it's in standard position is to identify the angle from the origin in standard position, starting position, which is from the positive x-axis. The angle turn from the positive x-axis to the vector. Stop. How much is this angle? And it could be answered in radians or degrees, whatever they ask us. So the direction angle theta of a vector v, or whatever name, you don't have to call it theta, and you don't have to call it vector v, but it's some angle, whatever you want to name it, and some vector, whatever you want to name it. Well, they did give us vector v, so I guess we should honor that and call it vector v. What about the angle? They don't tell us, but that's one of our more popular notations for angles, so I'm calling this theta. That's what we want. It's an angle that starts in standard position and ends in quadrant 2 somewhere. And they want it in degrees. So it's past 90 degrees and it's less than 180 degrees. So how do we find this angle now? Well, go back to the origin, the initial point of the vector that's in standard position. There is our vector. draw a right triangle using the component, the horizontal component, or the horizontal movement, or the number of I units, which is -7 of those horizontal unit vector I's, and 18 units vertically, or 18 of those unit J vectors. Either way, you're going to say, label this side -7 and this side 18. There's your right triangle. This is adjacent to this reference angle. This is the hypotenuse, which is the length of the vector, which we already know is the square root of 373. And we know the opposite side is the 18. So, to find the angle, the direction angle theta for the vector, for this vector, then we can use the reference triangle, specifically find the reference angle right here inside the reference triangle, call it theta prime, and once we know this angle, the reference angle here, theta prime, then we can find angle theta. So, you can use, I wrote it here. To find the direction angle theta of vector v, we first find the reference angle of theta, theta prime, using one trigonometric ratio from SOHCAHTOA. Well, let's see. This side we just computed to be the square root of 373. They gave us these two. I mean, they didn't draw the picture, but they gave us the vector in, so that's why I say later on they just start to say this is in component form. It's in component form, but written with I's and J's. Because they get tired of saying the vector written in standard position as a linear combination of standard unit vectors I and J. Whew, that's a lot to say over and over again. But anyway, so I would just use the two numbers they gave us, the adjacent being -7 and the opposite being 18, but you could use one of the SOHCAHTOA or CHOSHIKAO with the hypotenuse as well, as long as you don't make a mistake with this magnitude. So either way, so I'm going to pick the trig ratio that has adjacent and opposite in it, and that's either TOA, opposite over adjacent, tangent, or you can use cotangent. So, I don't know if I guess I didn't write down CHOSHIKAO, but cotangent would be reciprocal, adjacent over opposite. So you could use either tangent or cotangent. I'm just going to pick tangent. So, using tangent of your reference angle theta prime equal to opposite over adjacent. Now solve to get rid of the tangent. To solve for theta prime, we have to get the theta prime is locked inside the tangent, so to speak. So to get rid of the tangent, you have to put tangent of theta prime into its inverse, which is tangent inverse, or arctangent in front, and then you put it over here as well. These will compose out to theta prime, and then here you get either tangent inverse or arctangent, your choice, of 18 over -7. Now we go to our calculator and make sure we're in degree mode. And now we're going to type arc or tangent inverse, of opposite which was 18, oops, divided by negative 7, and we get negative 68. Let's see, what do they want us to round it to? 1 decimal place. Negative 68.7 degrees. Negative 68.7 degrees from standard position. We're right here from standard position, and we get negative 68.7 degrees. But remember, what that is, everyone, if you think about, it's because of the restriction on tangent inverse, or arctangent, which we talked about in chapter 4. It's been a while, although I guess it really hasn't, because some are to 5. Anyway, so arctangent or tangent inverse is going to give you an angle either backwards into quadrant 4 or forward into quadrant 1. So it gave us, because we wrote negative ratio, the negative tangent ratio has to be in quadrant 4, not in quadrant 1. So that's why it gave us this negative 68.7 degrees. From the positive x-axis this way is the negative 68.7 degrees. I know that's kind of a mess. But we don't want this one. We want we put tangent inverse of negative 18 over negative 7, and it gave us negative 68.7. Because tangent inverse is restricted to an angle backward in quadrant 4 or forward in quadrant 1. And so this angle is going backwards. It's the reference angle going backwards in quadrant 4. If we were to take away this negative sign, it would give us 68.7, but that would be the angle in quadrant 1, and that would be the reference angle in quadrant 1, 68.7. 68.7. But we want, so what I'm trying to say is, this angle right here is 68.7 degrees. It just, you don't say negative is all. This angle right here is the same reference angle as this one, or the same one that would be in this one. If we take away the negative, that's a little tricky to describe. You get positive. And now that would be the angle in quadrant 1. That would be this one. But we don't want the one in angle 4, backwards into quadrant 4. We don't want the one in quadrant 1. We want we're finding the reference angle right here in quadrant 2, but it's still the 68.7. So you just put that in there, 68.7. I hope that doesn't feel too uncomfortable. So now, if this is 68.7 degrees, then what's this one? Well, we know all the way from starting position to here is 180 degrees, but that's too far. So we got to back up the reference angle. So it's 180 degrees minus the 68.7. So the reference angle is a positive one, 68.7. A reference angle is always a positive angle. Now, if you turn him backwards like we did here, you say the direction is a negative direction, but the reference angle is still a positive 68.7 if you put it in a triangle. So then, how much is the angle from here to here, which is the direction angle of the vector v? It's 180 degrees minus 68.7, which is 111.3 degrees. And so, I hope that makes sense. So, from here to here is 111.3 degrees. And that's what we have right here. Okay, so if that makes sense, class. So here we go, moving along, either slowly or very slowly or at a nice pace. I don't know which. Hopefully not too fast, I don't think. Hopefully. 23, you have to be patient, everyone, to learn in life. Hope you're patient. We have to redefine what we thought patient is as we grow up, if we're going to continue to learn more and more sophisticated things. Okay, there was my 20-second lecture. 23, find the component form, oh, I've heard of that, component form of a vector v given its magnitude. Oh, there it is. The magnitude is 4 units long. We don't have to compute it. And they also give us the angle it makes with the positive x-axis. The angle it makes with the positive x-axis. That sounds familiar. That's what we just talked about in the last problem. The direction angle of the vector. The direction angle from the origin in the positive x-axis, the starting position of an angle, turn either positively or negatively, depends on what they tell us, and turn that many degrees, and that takes us to the vector. Unless we don't move at all. And that's what this one is. We don't move at all. The angle is 0 degrees. So we start, and there's the positive x-axis. We're looking out that way, but we don't turn. And now, the magnitude is 4 units. So if you're looking this way, it doesn't say look this way. That would be 180 degrees. If you were at the origin looking that way, then that means you would have had to turn, because you have to start looking this way in starting standard position for an angle. You're at the origin, you're looking in this positive x-axis direction. Not this way. And not that way. And not that way. And not any other way. Until they tell you to turn. You're starting. We're all starting in the same standard way. The same standard position. What is the angle? 0 degrees. That means don't move. Don't turn. You're still looking out that way, and now you move, you walk, you step, whatever the magnitude is, 4 units long, so 1, 2, oh, well, these are not 1, so it's 2, 4, so it's right here. So this will be the initial point of your vector in standard position, and the end point, or the terminal point, or the tail of the vector will be right here. So which one of these graphs matches that? Well, this one is going the wrong way. This one looks pretty good. Must be this one. Oh, must be that one. This one is if the angle was, as I mentioned, 180 degrees. This one would be if the angle was 270 degrees or negative 90 degrees. And then move down 4 units. This one, of course, would be 90 degrees, or pi over 2 radians, and so forth. So I hope you understand that it's this one. And now, write down this vector that's in starting position. Write the vector in component form. So what's the horizontal movement starting at the origin? Well, it's a movement rightward, 4 units. So we could say 4 units, or 4i, 4 of those I vectors, those unit I vectors, 4 of them. 1i plus, that's a second I, a third I, a fourth I. It's not I complex numbers, it's I vector. So we could say 4i plus, we don't move upward, we don't move downward, so plus 0j. 0 movement in the vertical direction, in the j unit direction. So it's 4i plus 0j, or if we put it in component form, you would put then here the vector symbol, the vector open bracket, and put 4, 0, and that's should do it. And there we go. And this one is also graded, saying that this one up here is correct. Not that this one's correct. The one we did is correct. Okay. Next, I'd like to help you with 24. Same directions, I think. Yeah. They give us the angle and the magnitude. Find the vector in component form. So the angle is 45 degrees in standard position from the, which means from the positive x-axis. So from the origin, you're looking out in the starting position direction, which is the positive x-axis direction, and then you turn positive 45 degrees. Well, we know positive is counterclockwise, and so this one's negative, so that's not it. So that's wrong. This one's 45 degrees. This one is not 45 degrees. The reference angle is 45 degrees, but this would be 135 degrees. It would be 180 minus 45, 135. That's not it. This is, again, a reference angle, 45 degrees, but it would be 180 plus 45 more, which would be 225 degrees, or it would be negative 135. But we want positive 45. So that this is the only one. So it has to be this one. You're like, wait a minute, what about the magnitude? The magnitude is 2 times square root of 7, whatever that is. Well, that's a little smaller than 3. So 2 times 3 is 6. So it has to be less than 6 units. Who knows here? But it's okay because none of these other ones are correct. So it has to be this one by default. So that's correct. Now we need this vector right here. Here it is. We need it in component form, which means we need the horizontal movement amount, this value here, and the vertical movement amount. Well, because this is a 45 degree angle, then these two sides are going to be adjacent. I mean, they're going to be the same amount because it's an isosceles. It's an isosceles right triangle when you have a 45, 90. That means this one up here will be 45. Let me show you my picture. So, 24. Given the magnitude of vector v is 2 times square root of 7 units long, units, the angle the vector makes in standard position relative to the positive x-axis is 45 degrees. So that's what I attempted to draw here. Origin, standard positive x-axis, turn positive 45 degrees. That's halfway from here to here, of course. There's your 45 degrees. And move out. Now go in this direction, whatever this 2 times square root of 7 is. So we just make it up. Just draw it. And there's the end of our vector v as a sketch. And now they want us to write down what is vector v in component form. Well, that means we need to know the horizontal movement and the vertical movement. I could have wrote h here and v for horizontal and vertical, or I could say, in terms of this triangle, the x value and the y value. they have to be the same number because, as I already mentioned, this is a 45, 45, 90 right triangle, which means the two 45 angles, the opposite sides have to be the same. There's more than one way to figure out what these side lengths are, but one way would be use one of the SOHCAHTOA ratios, because you have a right triangle, you know an angle, and you know one of the side lengths, so then you can find a missing piece using one of the SOHCAHTOA trigonometric ratios. So let's see, we have 45, we have the hypotenuse, we need the opposite, and we need the adjacent to the reference angle of 45. So just find one of them and then you have both of them, because again they have to be the same, only because it's a 45. Okay, well I just picked, okay, let's find this adjacent one. So we write down, to find the x value we can use from SOHCAHTOA adjacent over hypotenuse. Adjacent is x, hypotenuse is 2 times square root of 7. Adjacent over hypotenuse is cosine of the angle 45 degrees. And now we have a little equation here in which we can solve for x, which is the side we want right here, which is the horizontal component of the vector. So how do we solve this now for x? Well, to get rid of this, to solve for x, to isolate it, you need to get rid of whatever is near it. And what's near it, a division of 2 times the square root of 7. What's the inverse operation to dividing by 2 square roots of 7? The inverse to division is multiplication. So we're going to multiply both sides of this equation by the 2 square roots of 7, or 2 times square root of 7. Hope that's okay. 2 times the square root of 7 divided by 2 times the square root of 7 is 1, or 1 times what's left in the numerator, 1 times x. 1 times x, you don't have to write the times 1, so it's there if you want it, but it's just x as well. Over here now, you multiply 2 times the square root of 7 times cosine of 45 degrees. 2 times, sorry, it's kind of messy here. 2 times the square root of 7 times cosine of 45 degrees. Now, if they ask us to round it to the nearest whatever, then we put it in our calculator. And they don't say anything about rounding. So therefore, we have to write it in exact form. So, cosine of 45 from the famous 45 degrees, pi force is a famous reference angle, a famous angle. And like our first day of this semester, or the second day, I don't remember, but 45, we said we could use these famous numbers instead of using any bigger numbers. Oops, can't see. 1, 1 square root of 2. 1, 1 hypotenuse square root of 2. So to find cosine of 45, you say adjacent over hypotenuse. So 1 over square root of 2. So instead of cosine of 45, wherever I am, sorry, when I look at the screen and I look at my notebook, it gets me, my head starts to spin a little bit. So where am I? I am, oh gosh. So right here, cosine of 45 degrees is equal to 1 over square root of 2, adjacent over hypotenuse. Now just clean this up. Numerator times numerator times numerator is 2 times the square root of 7 times 1 is just 2 times the square root of 7. In the denominator, this invisible 1, if you want it, times square root of 2 is still just square root of 2 equal to x. We could leave it like that, but I think it's a good opportunity to get rid of the square root of 2 on the bottom by multiplying by the square root of 2, and then therefore on the numerator as well. Because if you do that, it cleans up fairly nicely, instead of leaving it like that. I didn't check, but maybe WebAssign will take that as well. But let's multiply by the denominator by the square root of 2 so that the square root will go away in the denominator. And if you multiply the denominator by square root of 2, you multiply the numerator by square root of 2, because this is an equivalent to 1, to multiplying by a 1, even though it doesn't look like a 1. What is the square root of 2 times the square root of 2 in the denominator? It's the square root of 4. What's the square root of 4? It's 2. So there we go. In the numerator, we have a 2 there already, so I just wrote it here. The square root of 7 times the square root of 2, you can put those together inside one radical square root symbol, and 7 times 2 is 14. So we have now this 2 that was there times the square root of 14, which changed because of the 7 times 2 now, divided by the denominator, which is a 2. And that was worth doing this, because now this 2 divides with this 2 to 1. 1 times the square root of 14, you can just write square root of 14 as a times 1 if you want it, but you don't need to write it, equals x. And this is much cleaner than leaving it like that, but it's not wrong to leave it like that. So I put the square root of 14 for the x value, which is this right here. So if this side is the square root of 14 units long, then this is also the square root of 14 units as well, because of the 45, 45. And therefore, how can we write vector v, whose the vector has direction angle 45 degrees and is 2 times the square root of 7 units long, magnitude, in component form in standard position from the origin, you say move horizontally square root of 14 units, then move vertically the square root of 14 units. So in component form, vector v is open vector bracket the square root of 14 comma the square root of 14. So I hope that makes sense. And that should be, well, I know I already put this one in, and it's correct. And we already checked the graph, so we're good. So I hope that makes sense. (25) is the last question. This was a lengthy, they all are, but a lengthy section. A lot of concepts. This last question is sort of a repeat of another question in the assignment, so I'm just going to remind you. They tell us to find a new vector, v. They tell you already the magnitude, it has to be 6 units long. And it has to be in the direction of this vector 3i. This is not v right here. This is just another vector they didn't name, and they said, and what is it? It's 3i plus 4j. So this new vector you're going to write down in component form needs to be in the same direction as this one, which is 3 horizontal units and 4 vertical units from the origin. 3 over 4 up. That's the direction vector. And our vector that we want to create is going to be in that direction. It's just going to be shorter or longer than that. 3i plus 4j would be right here. And by the way, that's a famous right triangle. 3 over 4 up. So the hypotenuse, or the length, would be 3, 4 up, so this would be 5. So the magnitude of this vector is 5 units. So imagine it goes over 3, up 4, stop. That would be the 3i plus 4j, and then from right where this mouse arrow is to the origin would be 5 units in length. And we want that same direction as I just I drew without drawing it. But we want it to not be 5 units long, we want it to be 6 units long, so a little bit longer. And then they want you to write that, find that vector, and then write it in component form. Well, it can't be this one. It's going the wrong way. 3, 4, and then it's a little longer than that. That looks pretty good. This is the wrong way. It's the wrong way. So this is the right one, but now we still have to write this down. And so to do this, I'm going to let you guys finish that one. So it's very much like this number 17 we did together. They gave us the direction vector -7, 24. And then we found a new vector that's in the same direction as this one, remember, but it had to be 75 units long. So this problem right here and the one on the bottom is the same exact strategy. And the one on the bottom, it was 3i plus 4j. And now make it a little longer than that, but in the same direction. So you can do the 25 using the same idea as this one. So I hope that's okay. The last few things to talk about are sort of cleanup problems, in that they should be fairly reasonable compared to these other ones in terms of time. There's some introductory questions that go over vocabulary. There's also these sketches that I haven't shown you, so I'd like to do a couple of these. Number 11, they give you two vectors whose initial point is at the origin, so these are in standard position already. They don't tell you what they are. They don't give you the component values. They just draw a picture. So the direction of u is this way. They don't tell us what the horizontal component is and the vertical component, but they just show us basically what it is. And the same with v. Now from that, sketch whatever this other new vector here is. So this one says negative vector v. Negative vector v. So negative vector v is the same thing as saying -1 times vector v. So what that does is that, everyone, just pretend that this was, pretend this was 2. Pretend this was, I don't know, 5. Just pretend. And so this would be 2 in component form, 2, 5. And that would be, and that's vector v. Just pretend. Then what would this be? -1 times v would be a brand new vector. A brand new vector. And you would say -1 times 2, 5. And that would be, in component form, -2, -5. -1 times 2, -2, -1 times 5, -5. Now where would that be? Well, instead of 2 to the right, would be 2 to the left. And then instead of 5 up, it would be 5 down. Pretend that's vertical. So whatever, just kind of sketching. And then this would be negative 5. So then you would go negative 2 and negative 5, and you'd be right down here somewhere. And then from standard position, you would, now I just made a sketch, but it's supposed to be straight. And it's supposed to be in the same direction as this vector v, but just the opposite way. It has to be still. If you multiply a vector by any number, any scalar, they call it a scalar number. It's because it scales. It either makes this longer or shorter, but it still preserves the direction. Well, when I say the direction, you should be careful because you can also go in the opposite direction, but it's still on the same linear path. It's just going in the other direction. Okay, so it's the opposite direction, but still on this pathway. And it's just going this way, and it's the same length as this one, because we multiplied only by, it's a negative, which changes direction, but times 1 does not change the magnitude. So then it has to be something like that, which will be your negative v vector. So which one is that? So it's not this one. It's not that one. It's not, this is going in the same way. That's incorrect. It has to go this way, in the opposite direction. There's the arrow thing that shows you that's the terminal point, and now the terminal point for this vector negative v has to be the other way. So that's what's wrong with this one. Well, plus the initial point has to be at the origin. So there you go. Check. And hopefully we clicked this one, and there's the green check mark that says this one we clicked is correct. So good. I'll let you do this one. I'll let you do this one. I would like to show you this one, 14. Consider the same two vectors again, u and v, in standard position. And now we're going to combine them. U vector u minus vector v. So we haven't talked about this yet. And so this is what you do, or this is what you can do. When you add vectors together or subtract them, you can start with whichever vector you want. You can start with the first one that's written down, or you can start with the second one, and either way you'll get to the same result. But I'm going to start with the one that's first, which is, okay, start in standard position at the origin, move out to the terminal point or the tail of vector that's written firstly, which is vector u. Pause. Get your coffee, have a drink of coffee or tea or water or whatever. Reflecting on our lives. Try to hang in there tough for the rest of the course. Okay, we had our pause. Now what are we going to do? From this tail position, the terminal point of the first vector written down, now you're going to move relative in the direction to whatever this is written here. If it was plus v, like this one, plus v, if it's plus v, then you would go to the tail of the terminal point of vector u, pause. Now take this vector right here, a positive vector v, which is just the same as this. Pick up this vector, pick it up off the grid, off the screen, hold it in your hand, and take the initial point, take the whole vector, but with the initial point you place it right at the end of this first vector that was written firstly. So right here, and now you put, because it's not minus vector v like the other problem, but positive vector, now you just move this vector and it's the same way as it was written here, but you just moved it over here. And so now I'm going to butcher probably trying to draw that. And something like that. And that's vector v. And now start, what is the result of taking vector u and adding vector v to it? So you go back to the beginning of your first vector, which was u, which is at the origin. Oops. And now you draw a vector that ends at the tail, the terminal point of the second vector that you just moved over and attached. And so if which I'm really struggling here. That's really sad. So that vector right here, everyone, is called vector u plus vector v. That's this right here. So now, which one is that one? The initial point is at the origin, and the terminal point is right here at the terminal point of the second vector that you placed onto the end of the first vector. Phew! And so this is not right. This is the wrong way. It has to be the other way. So here we go. There is u plus v. So this is like a trap. This is vector v moved over, which we needed to do. But then the result, or they call it the resultant vector, take one vector, add or subtract another vector, and now you have the result of the two from the origin to the tail of the second one, and now you have a new vector, which is the result of the two vectors being added or subtracted. Resultant vector. And it's this one. And there's our nice green check mark. So this one, same thing to start. Vector u, go to the end terminal point, the tail. Now bring this vector here, the second one. But before you bring it over, you have to realize that it says negative vector v, which is the one that we just drew a moment ago down this way. And so when you don't pick up this vector and move it over to this terminal point, you take the negative vector v and you move it over to this terminal point. And when you do that, it's going to be right here. Well, something like this. And so when we do that, if I can, again, pretend that's negative vector v. And now the result is from the standard position to the tail to the terminal point of the second vector that you added on. You say, wait a minute, we subtracted, but, or you can think of it as an addition of the negative vector v, is what you want to think of it as. And now draw a vector from standard position to that terminal point. And here is the vector u minus v. So this right here is this right here. Initial point, terminal point, with the arrow that way. That's the direction of this combined u minus v. So, which one is it? So they're going to try to confuse us, of course. So I have to erase this to scroll down so that you can see it. And so it erased, as I said, but those two are wrong. And so I hope you remember that it's this one. So this was the negative v, and then we started from the starting position to the end of the negative v. Like, what's this part for? That's if you would have gone the other way and you would have started with this negative vector v first, go down at the terminal point of this one, put the other vector u, move this initial point, move it right here, and move in the same direction as vector u is, and that would also get you to the end. And this would be then you'd have a little arrow here, and then you'd come from here to here, just like that. So you end up seeing this parallelogram all the time, because you could go in two different orders. Start with the first vector and attach the second one, or start with the second one and then attach the first one. So it's this one. So I hope that's okay, class. This is the same kind of thing. Take vector u, but now they tell you what it is. They still draw it though. Well, all of them have the same u, so they drew the correct u, 3i minus j, 3i minus 1j, that's this one. Vector w is 1i plus 3j. That would be right here, but then they multiplied by 3. So there's the 3w, the 3w, the 3w, the 3w. Now add vector u plus 3w. So I'm going to let you guys pick that one. So that takes care of that. And I believe same idea of this one, except it's shorter. You take this vector u, which is defined by a linear combination of I and j, 7 over down 1, and then multiplied by this fraction, 8/7. Well, 8 over 7 is a little bit bigger than 1. So that means the vector v is going to be a little the same direction as this one, but just a little bit longer. So now you can figure out which one that has to be. And then the only thing out left is some terminology, 1 through 5. Just want to make sure so all of these should be fairly simple. I'll just pick one. Oh, this one. The directed line segment PQ has blank P. So what's P called? Directed line segment PQ. P is called the initial point, and Q is called the terminal point. And I don't know why it does that. Oh, it's right up here, that's why. And so the other 4 should be just as simple. Okay, class. Well, I got tired. I'm sure you might have as well, but you can pause it and come back and do whatever you need to. 3 hours and 15 minutes, a long lecture. So I apologize, I'm getting a little tired here. But we are done, and that's all. That's everything. Well, that's a lot. That's a lot. So, but I hope it all makes sense, and I hope you're able to not only understand all these concepts, but now you're able to successfully finish your assignment and yeah, do well. Okay, so I will be making the next video over section 6.4, which is the second of 2 only sections that are on vectors. And that one is going to be much shorter than this one. There's many fewer topics, albeit they are important topics, but there aren't as many. So that should be a relatively short section and relatively quick to do. Okay, everyone, so thank you for your patience. I hope this can be of help to you, and we'll see you next time. So this is Mr. King, of course, saying goodbye for now. Okay, bye, class.